Let's continue with filtered Fourier modules. So prove the following proposition. So given a short exact sequence of Fourier modules zero to d prime to d double prime 0, then we have the Newton number of d equals the number of d prime plus the number of d double prime. So it's not additive. Secondly, prove that for given d1, d2 Fourier modules, then the number of the tensor product of Fourier modules. We have defined what is this tensor product of Fourier modules, again as a Fourier module, equals dimension of d2 times the number of d1 plus dimension of d1 times the number of d2. In particular, Newton number of d1 self-tensor equals r times dimension of d r to the power r minus 1 times the number of d. This comes from the induction or iteration for any r bigger or equal to 1. Thirdly, if d is a Fourier module, then the Newton number of its due equals minus the Newton number of d. Solution. First part, it's about the determinant of matrix. Comes from the Frobenius, right? So let u1 until h prime be a basis for d prime, and let A be the matrix for phi d prime under this basis. And then we extend this basis of d prime to a basis of d, because this is a submodule of d. Let's say dimension h. Extend the basis from d prime to d, and then as d2 prime as a k0 vector space, this is just d quotient d prime. In particular, this gives you a basis double prime. Okay. Now let's write down the corresponding matrix. So for phi d double prime, let's say it's associated matrix. Let's suppose it's B. And then what is the, so you have over this part, you have phi of d prime, which corresponds to A. And for this part, you have phi of d double prime corresponds to B. And so for phi d, the matrix should look like under these fixed spaces. Here is A, and here is B, something here between. So we have the determinant of, let's call this C, determinant of phi d of C equals the determinant of A times the determinant of B. And so the Newton number of this extension of d prime and d double prime, d equals, by definition, the VP valuation determinant of C, which is then the VP valuation of determinant of A plus the VP valuation determinant of B, right? And so this is d prime plus d double prime. Second, let's talk about the Newton number of tensor product. So we have to talk about the determinant of this corresponding matrix. Corresponding matrix of this tensor of Frobenius should correspond to the Kronecker product of matrices. So let EI bigger equal to 1 less equal to H1 respectively FG be a basis 41 respectively 42. And then let A respectively B be the matrix for phi d1 phi d2. Okay. Under this basis. So now we have EI tensor Fj forms a basis for d1 tensor d2. And the matrix for phi d1 tensor phi d2 is a matrix given by the Kronecker product of A and B. So let's quickly recall. So this A tensor B should be A11B, A12B, A1NB, AN1B, right? ANNB, this matrix. And this also a fact tells you how is the determinant of this Kronecker product relation with the determinant of A and B. The relation is given as follows. Determinant of C would equals to determinant of A to the power size of B, which is the dimension of D2, time the determinant of B, determinant of B, dimension of D1. Therefore, conclusion, the Newton number for D1 tensor D2 equals, by definition, the p-adic evaluation determinant of C, but this is then dimension D2 times the valuation of determinant A, which is then Tn of D1 plus, similarly, Tn of D2. And so we are done. Last exercise. Suppose phi A, give its basis, phi D, give its basis A. Then how about phi du of D? Recall what's the formula. In the last exercise, exercise 85, we have discussed this due object and its formula. So recall that phi du maps eta to sigma eta phi inverse. And so this should tell you that if the matrix for phi d is A, and the matrix let's say under a fixed basis EI, then the matrix for phi du under basis EI du for D du is given by sigma A inverse, right? So because here basis is mapped to this, while here you have E1 du, ED du, this is mapped to A inverse, and then there is Frobenius acting on U. On the coefficients is just just on the coefficient. Wait. The question is this the same as right, this is what we claimed. Right. This is what we claimed. So how do you do that? So recall phi du of eta is sigma eta phi inverse, right? Eta is from home, d to k0. So the du, and here we have a basis ei. And so this is saying that it's totally linear algebra. So let's just check it on basis element. So question, sigma eta phi inverse over base element. Is this the same as E1 du? Wait. We claim that the matrix for phi of du under the basis is given by sigma A inverse. So we're looking at phi of du. Yeah. So the question is, we only need to check it on those basis elements. This is phi of du. That's how it maps. The question is, so this phi of du is mapping E1 du, ED du to sigma E1 du compose phi inverse, sigma ED du compose phi inverse. The question is this the same as E1 du, ED du? Multiplication with the matrix sigma of A inverse, right? How do you check that true or not? You check it on its valuation. Let's pick this. Check its valuation on basis element EI. So this is what this is. Sigma compose E1 du compose phi inverse UI. This would be so. A1 ED, and then multiplication with the i's column, AI1, A1I, A2I, ADI, right? Let's see, one compose E1 due compose with summation AJI EJ. I is fixed, so J from 1 to D. And so finally this is the sigma of, only pick out E1. So J must equal to 1. AJ1. Sorry, A1I. This is what's in section. As equal to a yes. On the other hand side, let's look at this part. So the first component is here given by, so the first column, first row, first column, yeah. Sigma. How do I write that? So for A inverse, let me write A inverse A inverse 2 1, A inverse D1. It's the matrix and gives you sigma A inverse 1 1 E1 due plus sigma A inverse D1 ED due. And this apply on EI. Let's call this is an element again in the home from D to K0. Let's call this F. Then F of EI equals sigma A inverse 1 1 E1 due blah blah. And so obviously it's only the EI due left. So what is left is sigma A inverse of I1 so one is sigma of A1I, the other is sigma A inverse I1. Have they given you the same result? Wait. Let's find U, defined using this dual of basis. And we ask what is the matrix with respect to this dual basis? Is this sigma of A inverse? Okay, sorry. So here is a mistake. We use phi inverse times EJ, so here it should be, let's just say A inverse, let's call it Bij to simplify notation. and then this is both. This will change, so this is just b1i, b2i, bdi, and finally what you got is bji. What you got is b1i, and here similarly we don't use this strange notation. We're talking about sigma A inverse. So sigma A inverse, as we said, this is A, and we use B. The first column is B11, B21, BD1. What you got here is summation sigma B I1 E I due from 1 to D. And so when we check this, we'll check with B11, BD1. Finally, what you got is sigma B I1. 1 is B1I, 1 is BI1. Seems not the same. Let's think about it again. This is the phi inverse. We're checking both parts on EI. Checking both parts on EI. What is phi inverse of EI? Phi inverse of EI is the ith column of this. The ith column so we pick out the ith column. The only one, j equals 1, and so it's left with sigma B1I. Well, on the other hand, we have this. With the same matrix sigma A inverse. we're checking whether the first column of this matrix multiplication. So here we pick the first column of the corresponding matrix sigma inverse, should give us the image under phi du of u1 du. So bi1 times ei du. This element as element in the du of d, when you evaluate again, test it on arbitrary base element ei, it gives you select only those ei, so comes ei, the coefficient is sigma b I1. So this is strange, does not match. I guess there's some mistake. It's not necessarily a symmetric matrix. Let me check one more time. So fixing the matrix A for Frobenius under the basis EI. So phi d of E1D is mapped to E1D multiplication with A. And the question then, what is phi d du? Acting on this du basis gives you here. It's claimed that this should be put this matrix there. Let's check it. So by definition, this phi d du acting on an element is given by sigma composed with eta composed with Frobenius inverse. In particular, it maps EJ du to sigma composed EJ du composed with phi inverse. And so just it's enough to justify down all those EJ du. This is telling you that this is the map for phi du. Now the question is this also the same as this matrix multiplication? And so we have to check component by component that is the same. When we're checking they are the same, notice they are again they are linear maps. We have to check it on the basis of the space they define now, which is D. So we pick basis EI, and then we check. For example, let's check the first component. So the first row, first component is sigma E1 du for the inverse with map with X on arbitrary basis element EI. This gives you sigma composed with E1 du composed with Frobenius inverse acting on EI. Yeah, what should be that? Frobenius acting on the multiplication by A, and Frobenius inverse acting on multiplication by A inverse. So here we should be put this position. We should put A inverse. but we're not picking the first. Yeah, we're picking the ice column. We're acting it on EI. Ice column. This is the ice column. So what we got is finally B1I E1, B2I E2, B3I E3, etc. And what is left is only B1I E1. That is B1I. On the other hand, if you start with this E ideal, do put this A inverse here, sigma of A inverse. What do you got? Still you got a couple of elements in this dual space. AI1E1 dual. Yeah, for I, from 1 to D. And when this element you evaluate on basis element C, again EI, you pick out B I1, and so finally what you got is sigma BI1, not necessarily sigma B1I. So left hand exercise to find what's missing here. What's wrong here? What's wrong in the computation? And suppose this is true, we find a mistake. So I'm confidently that it should be modified. This is the case. Then finally, to conclude the argument, sending us the Newton number will be p-adic evaluation, the determinant of the sigma A inverse. Yeah, what's the argument here? Or maybe we are not wrong, we are correct, but the final conclusion is actually it should be sigma of A inverse transpose. Yeah, by what we have computed actually is this one, and then it's just the transpose put here, but it doesn't influence the determinant. And so this is again just determinant of A inverse. The similar reason, because so one more step, this is the sigma of determinant of A inverse, and it's the same, this is element E again in WK. inverse equal K0. This equals the p-adic valuation of the determinant of A inverse, which is then minus the valuation determinant of A, and hence this is minus the number of D, the Newton number of D. So basically what we have proved is actually, it's not this, but the transpose of it. Right, that's what we have proved.